So this is problem 22.20 from homework 1, and they've given us this figure here, and they want us to determine the magnitude of the force on the 1.0 nanocoulombs charge. So the magnitude of the force acting on this one. And in my figure I've drawn, we know this is a positive charge, so it's going to be repelling that one. So that charge, or that force, is going to be pushing away from the other positive charge, and then the negative charge is going to be attracted to. So for that one, it's going to be, the force is going to be going towards the negative charge. And then to find the magnitude of our forces, we want to first find the magnitude of each of these forces. So starting off, to find the force of that 2 has on 1, we just want to use Coulomb's law, which takes the constant K and then you multiply the charge on each of those particles and then divide that by the r squared. So yeah, for that one we've got the force of 2 on 1 equal to that constant K times the charge of 1. Oh yeah, I've labeled these 1, 2, and 3, obviously. So yeah, the charge on force 1 is 1.0 times 10 to the negative 9 coulombs, or 1 nanocoulomb. The charge on force 2 is 2.0 times 10 to the negative 9 coulombs, and we're dividing by that r squared, which I've converted to meters so that we can cancel. And for that one we get the force equal to 1.8 times 10 to the negative 4 newtons. And then we do the same thing for that force of 3 acting on 1. So the force of 3 acting on 1 is equal to also constant K times Q1 times Q2 divided by that r squared, and we get the same force because you can see here we're taking the absolute value of a negative and a positive of the same number. So both of those forces are equal to 1.8 times 10 to the negative 4 newtons. And then next, because they want the magnitude of the net force on 1, we can't just add these two. We need to break this into its vector components in order to find that magnitude of both of the forces. So starting with that first force again, the force of 2 on 1. So if we break this into, if we lay it out on an x coordinate, we have that force, the force going towards that that number 1, and then we have our y component, so that's going to be the j hat direction, and then the x component is the I hat direction, and we want to find these two vectors here so that we can add them to the other force and find our total net force. So for this first one, we know to find the force in the I hat direction or in the x direction, we just take the magnitude of the force multiplied by the cosine of theta, which we know theta is 60 degrees. And for y, we're going to take the force times the sine of theta. And then we just use this equation here for our unit vectors. And this is going to be what we use. So we take that first force of 2 on 1. We know the force is equal to our 1.8 times 10 to the negative 4, which we calculated, and multiply that by cosine of 60, and that's going to be in the I hat direction. And same thing for j hat direction using sine. So the magnitude of the force of the vector in the I hat direction for that one is 9.2 times 10 to the negative 5 newtons, and in the j direction it's 1.5 times 10 to the negative 4 newtons. So that's going to be that j and I right there. And then we need to do the same thing for that second force acting on 1. So for that one, drawn it out again. And for this one, we need to be careful because, as you can see, the vector is pointing in the negative j hat direction. So we need to make sure that we subtract the j rather than add it. for that one. So for force 3 on 1, same thing, we take that force, times it by the cosine of 60 in the I hat direction, same minus the j hat direction, and we get, oops, that's supposed to be a minus there, but yeah, we get 9.2 10 to the negative 5 I hat minus 1.56 10 to the negative 4 in the j hat direction. So now that we've broken this into our vector components, now we can add all those forces together in order to get our total net force for that first particle. So we know net force is equal to the forces added together. So we take those two forces that we just found in our components, and we get a net force equal to 1.84 times 10 to the negative 4 newtons. So this might throw some people off, the fact that it's the same number as the forces we calculated for these two, but that's just this specific type of triangle, I think. But yeah, that wouldn't always be the case. So make sure that we always break it down into those components in order to find our total net force. And we can see that our net force is just acting in the I hat direction, so it's running positively along the x-axis. So for part B, they wanted us to figure out the direction of the force on the charge, so it's going to the right. And yeah, that all ties into what we're learning in chapter 22 with Coulomb's law and electric forces, and also brushes up on vector addition from 251.